In the previous videos, we have learned about the phenomena of electromagnetic induction, and we have written the rules of electromagnetic induction, right? Now, what we have written that the induced EMF, if this is the induced EMF, then that induced EMF was equal to negative of the rate of change of magnetic flux with respect to time. So there we had put this negative sign. So what is the meaning of that negative sign? So I have told you that I will tell you this later on. Now here it comes. So we can describe the meaning of this negative sign using this Lenz law. Now what the Lenz law says? Now the Lenz law says that the direction of induced EMF, the direction of induced EMF or induced current. Now, whenever you change the magnetic flux associated with the circuit, and that will result in an induction of induced EMF and current. But the question was that what will be the direction of the current? So here we are determining that direction of current. So Lenz law says that the direction of that induced EMF or induced current is such that it will oppose the change that is producing it. Means whatever the factors that are here or in the given situation that is producing that particular current, so the current will be in such a direction that it will oppose the change that is producing it. So let's look at the example. Now suppose this is a coil. Okay, now this is a metal loop. Now suppose if we have a bar magnet. So we have this bar magnet, north pole, south pole, right? Now when you try to move this magnet towards the coil, now what will happen? The flux that is associated with the coil, now that flux will increase, because as it is moving or approaching towards the coil, so the flux will naturally increase. This means there is a change in flux, right? Now when there is a change in flux, now what will happen? There will be an induced current. Now the question is that what will be the sense of that induced current, whether it is clockwise or anti-clockwise. Now look at the Lenz law. Lenz law says that the direction of induced current will be such that it will oppose the change that is producing it. Means the current will be induced in such a direction that it will not let the magnet to come closer. So how it will stop the magnet or how it will not let the magnet to come closer? So that is by making the top face of this coil as a south pole, right? Now as I have shown this symbol as S with these arrows, so you will say that the direction of induced current will be clockwise. Now when the current in the loop is clockwise, so this pole, the upper face of this coil will become south pole, and south pole both will repel each other, right? So when you try to move this magnet towards the loop, so what will happen? Due to the repulsion of the south pole, for the south pole you have to exert the force, and due to the exertion of this force you have to do basically the work against this repulsion. Now when you are doing the work against this repulsion, means you are supplying energy to the system. So the current that you are looking here, or the EMF that will get induced in the loop, so that EMF, that is basically the work done per unit test charge. So that EMF has appeared due to what? The work that you are doing, right? So from here we can infer that the Lenz law is basically based on conservation of energy. It is based on conservation of energy. Now in the same sense, if you try to pull this magnet up, now when you try to pull this magnet up, means you want to decrease the flux associated with the loop. Now, in such a situation, what will happen? The current in the loop will get induced in such a way that it will not let the magnet to move away. So for that, the upper face of the coil should become north pole. The upper face of the magnet must become north pole. So when I'm showing the upper face as north with these arrows, so it is clear that the direction of current will be like that. Then the direction must be anti-clockwise. If the upper face becomes north, so it will not let the magnet to move away, means it will pull. Again, you have to apply the force, right? So in this sense, whenever you try to change the flux, listen carefully, whenever you try to change the flux associated with a coil, there will be a current which will not let you to change that phenomena or that factor that is actually causing it. If it is the movement of the magnet, the current will not let you to move that particular magnet, right? We can understand this law in other form also. See, now this is the loop, this is the bar magnet. Suppose this time we take north pole downwards. Now, when you try to move this magnet towards this loop, this means there is an increase in flux. Increase in flux that is associated with the loop. And the magnetic field due to this magnet here is in this direction, right? So that magnetic field is due to the magnet, this bar magnet. Okay. Now, when you move this bar magnet towards this coil, what is happening? The flux is increasing. Now, there will be an induced current. Now, that induced current will not let the magnet to come closer, right? So, we have learned it from here that it will not let it come closer. Now, what this induced current will do? So, this is north pole. So, here we will get a north pole, right? So the direction of induced current will be like that. Now what this induced current is doing, this is the induced current. Now what you should do, you should use your right hand, curl your fingers of the right hand in the direction of the induced current. So when you are moving your fingers in the direction of induced current, the thumb is pointing towards what? The field. So due to this induced current, a field will get produced, so that we will call the induced magnetic field. Now this induced magnetic field will oppose the field of the bar magnet and hence reducing the field across the loop, right? Now similarly, check this situation. This is the loop. Now this is the bar magnet. Now when you try to pull it up, right? So due to this bar magnet, the magnetic field due to the bar magnet is in this direction, and if you are pulling it away, this means you are now trying to reduce the flux. So current will set up in such a way. So if it is pulled away, so here you will get a south pole, so that it will attract the magnet and will not let it go. So the direction of current will be like that. Now curl your fingers in the direction of the induced current. Curl your fingers in the direction of induced current. Now look at the thumb. The thumb is pointing down. So the direction of induced current is clockwise and the thumb is pointing in the downward direction, means the induced field is now supporting the already existing field, means it is now increasing the flux in that region, means making this south polarity much stronger. So whatever you do, either you pull the magnet away from the coil, or if you try to push the magnet towards the coil, whatever you do, whenever there is a change in flux, that change in flux is resisted by an induced current. It will not let the magnet to move towards or away from the coil.